Welcome to this lecture on energy and comfort results analysis.
Within this lecture, I'm going to present a short recap regarding the goals and the method applied in building thermal simulation. A part of the presentation will be dedicated to clarify the relevance of data visualization in building simulation. Then I will introduce the data visualization approach. I will close with some example of thermal comfort and energy results representation. As already discussed in the previous lecture, building simulation software can be used for different purposes: peak thermal load calculation, energy demand analysis, and thermal comfort analysis. In peak thermal load calculation, simulations are normally set for the extreme design days and generally used for sizing equipment such as chiller or boilers. Regarding the energy demand analysis, simulations are conducted for an extended period of time, normally a season or a whole year, using weather file with the aims to verify the building response, such as energy demand, to the entire range of conditions expected at particular site. Simulations are also used for predict the user comfort sensation in terms of predicted percentage of dissatisfied in the different building zones. In all the cases, the output data representation is very important in order to understand, share, comment the results, and if necessary, persuade the client. The simulation process is generally composed by four main stages: problem identification and definition, conceptual model development, simulation runs, results analysis and data reporting. Report generation and data visualization is a critical link in the communication process between the modeler, the designer, and the client. Why is data visualization important? In detail, the data visualization is the practice of translating information into a visual context, such as map or graph, to make data easier for the human brain to understand and pull insights from. The main goal of data visualization is to identify patterns, trends, and outliers in large data sets, as building simulation results are. Data visualization should provide a quick and effective way to communicate information in a universal manner using visual information. The practice can help designer addressing morphological or technical factors, or policymaker identify which factor affect energy consumption trend, pinpoint areas that need to be improved or need more attention. Selecting the proper way of data communication requires experience and to know exactly the scope of the simulation and who is going to read the report. A reader should understand the key takeaway in a moment, even if the model and the simulation results are very complex. Dynamic building simulation represents a powerful tool to support designers in high energy efficient building design. Nowadays, simulation tools are characterized by high level of detail and high reporting flexibility. Simulation runs usually generate a big amount of data, considering the following three reasons. Modeler can select any variables available as output, and normally the programs are allowed to calculate hundreds of it. Modeler can detail the geometrical building model with many thermal zones, increasing then the output numbers. Moreover, the user can specify output at different time steps like monthly, daily, or hourly. If we think to hourly simulation for each selected output variables, the modeler has to deal with 1,760 data, one for each hour of the year. It is clear how the dataset will increase, enlarging the number of thermal zones and the number of variables required for each of them. Again, without a graphical representation, no one will be able to read and understand such amount of data. Data visualization enables decision makers to see analytics presented visually, so they can grasp difficult concepts or identify new patterns. Here in detail few concepts regarding data visualization that the designer or the modeler must consider. Know the target audience. This shouldn't come as a surprise. Designing a chart of a graph should always be done based on the audience that will view it. Create a goal, or more like a logical narrative. Ensure to set clear goals that must be conveyed through the infographic. Choose the right chart type accurately. A pie chart does not complement every information visually. Similarly, a bar graph does not show every statistic clearly. Context. The use of color is encouraged depending upon the context. A decrease in energy efficiency could be marked red, whereas green could show the increased parameter. Use tools. One of the easiest ways to create data visuals is using tools. Use them as they make the charts intuitive as well as easy to read. Data visualization is the presentation of data in a pictorial or graphical format. It is even more so when we are trying to understand and interpret data or when we are looking for a relationship among hundreds or thousands of variables. Visuals stick in the long memory and improve comprehension, a key factor in interpreting data. Two types of data are normally analyzed in building simulation: qualitative and quantitative. Qualitative data refer to data sets that can be classified or categorized, like satisfaction score, but no data can be measured. A qualitative data is called also categorical, since can be grouped according to categories, such as temperature above 26 degrees Celsius or temperature below 20 degrees Celsius. These type of data are important in determining the particular frequencies of trace. The best charts for qualitative data are histograms, column charts, and pie charts. Quantitative data refer to datasets that can be measured. A typical quantitative data analyzed in building design is represented by the temperature level or by the energy use intensity. The best charts for this data are line charts, bar, and column graph. From the previous slides, we clarify how the graphical display of numerical data is an effective way to communicate trends, errors, and breakdowns. Considering the analysis typically required for the nearly zero-energy building design optimization, the modeler can use a set of specific charts as reported on the right side of the slide. A line chart is helpful in showing the annual temperature level trend of a representative thermal zone, while a scatter plot is welcome for comparing the thermal loads variation according to the external temperature fluctuation. Monthly heating and cooling energy analysis compared with on-site energy production is graphically well represented by means of bar and line chart. For verifying the energy balance, a graph showing the energy demand versus the on-site energy productions represents an effective communication way. However, the modalities of data representation can vary in function of the scope of the simulation and from the target audience. A specific task in building simulation is related to the thermal comfort level analysis. In this respect, the line chart representing the temperature fluctuation in a zone do not clearly show the intensity of the perceived potential discomfort. The European Comfort Standard EN 17730 and EN 15251 present a method for predicting the overall thermal sensation and the degree of discomfort. One of the comfort statistical index used by the standard is presented by the PPD, that is, predicted percentage of dissatisfied. The PPD is a good parameter for defining in a quantitative way the comfort level in a specific building zone. Three comfort categories are individuated: 1, 2, and 3. Class 1 means that no more than 6% of the people inside the zone will be dissatisfied by the thermal environment, while Class 2 and Class 3 means that respectively maximum 10% and 15% of the people will be dissatisfied. According to this, the figures reported on the right side of the slide can be used as an example for a graphical representation of the thermal comfort level. The charts can help designer investigating the impact of different energy conservation measures on expected thermal environment quality. The chart at the top right represents the thermal comfort according to the EN 70-70-30. The horizontal black and gray lines represent the comfort limits for winter and summer, and the green dots represent the hourly operating room temperature level of the analyzed building thermal zone during the year. This approach is applied for building with heating and cooling system. The chart at the bottom right represents the summer thermal comfort expectation according to the adaptive comfort theory. defined by the EN 15251. This chart can be applied for evaluating the summer comfort condition in a building without mechanical cooling system. Counting the number of hours outside the specific acceptability thermal comfort limits allows to compare and classify the expected thermal sensation in a building or a specific thermal zone of it. The present slide presents a so-called thermal comfort footprint chart. This graphical representation is applied for visualize in quantitative way the expected thermal comfort level inside a specific room. The charts are normally built separately for summer and winter season in order to check how the building is expected to perform during both cold and hot season. The temperature level is grouped considering the three comfort categories 1, 2, and 3 and displayed using bar chart. For each category is reported the percentage of hours respect to the total that fill in class 1, 2, or 3. An high percentage of hours within the comfort category 1 means an optimal thermal comfort expectation, while a high number of hours in category 3 means low comfort expectation. The use of correlation metrics is a good method for data analysis in building simulation. This procedure allows a quick identification of relationship between different variables. Correlation matrices are used as a way to summarize data and easily compare the potential energy saving of different energy conservation measures. In these slides, two examples are reported. The first chart on the top right shows how different envelope insulation options perform in terms of thermal comfort and heating useful energy. From the chart, it is easy to see how the option 6 allows high thermal comfort level with high energy demand, while the option 1 is characterized by low energy demand and high thermal discomfort. The chart at the bottom right shows another example of simulation output correlation. In this case, energy production, energy demand, and comfort level by means of exceeding hours of comfort limits are presented together. The black dotted line illustrates the target or the optimum level, and the green triangle represents how the building under investigation is performing. If a poor performance respect one of the three variables is detected, the designer can change some building parameter for increasing the building performance. Both the representations are helpful for guiding the designer and modeler during the building design optimization. Thank you very much for your attention.